specifically mention the uh, bivariate. We specifically mention the bivariate distribution. We see because sometimes we may be interested, maybe the actuary may be interested in obtaining an information from different two-dimensional random variable. We see that is why it is important to also look at the bivariate distribution, and we said that uh, the ones we've looked at, both the discrete and the continuous distribution that we looked at initially, that involves the Poisson, the binomial, the Weibull, and the other discrete and continuous distributions. We see that they all deal with one-dimensional random variables, one variable, and we see that let's say an actuary is interested in observing uh, two random variables, uh, probably because he needs an information from the two of them. We see that it is important for the actuary to consider two of these random variables. Say, for instance, in the medical sciences, the health of a patient might depend on the nutrition intake and also the cholesterol level, and then maybe uh, some other useful characteristics or attribute or information. So in that case, we have no choice but to use a more than one dimensional random variable. So either a bivariate or a multivariate. I would say that a bivariate has to do with two random variables. We also explained that we talked about the bivariate distribution PMF. We also talked about uh, the marginal density. We see uh, from the joint probability density we can obtain that the joint has to do with both the two random variables. So from there we can get the marginal density from the joint from the table from the marginal distribution table we can get do that. And we also talked about uh, joint distribution for single case and for continuous case, and we also talked about some examples on using the marginal distribution even as it relates to actual science and actual mathematics. So today we're going to continue in that regard on still under the estimation and series, but this time we want to consider the bivariate moments and the definition of raw and central product moments. We will look at all of this, and then we will see how we can see some examples, what they mean, and then basically we'll be doing this more. We'll be looking at more on the application, but at some moment I'll just take us through to the mathematics of it so that we'll see one or two how these things are computed or generated mathematically. Then before we can now come back to uh, how we can we'll now come back to our the main application. So I'm going to start now. At some point, I'll stop sharing this particular slide, and then I'll refer us back to the different material that will help us to see the mathematics behind it. Then we'll just take a glance. We may not actually uh, delve into the mathematics deeply, but we'll just see a glance and how it works and how it relates. Then we'll now come back here to this particular slide and look at the examples as it relates to uh, actual maths. So, probability theory and distribution, lecture 8. I'll be looking at bivariate moments and definition of raw and central product moments. Uh, so, here are the outline. In our outline today, even though it looks brief, but there are a lot of things we'll cover here. As you can see, we have 35 slides for today. So we have introduction, we'll look at bivariate moments, and we'll look at some practical examples and bivariate moments in natural science. So we understand what it means to what it means to what we say by moments, just like the moments we know about, the normal moments we have, I'm sure we have known of the arc moment, the first moment. We see that the mean is the first moment, the variance is the second moment, the kurtosis, the skewness is the third moment, the kurtosis is the fourth moment, and so on and so forth. So, and then we know that we use the moment generating function to generate all these moments. So, but we'll be seeing, we'll digress, we'll not digress, but we will look how, on what they really actually mean, what these moments actually mean, and how we can use them practically, not just the mathematical aspect of it. So, introduction. So, definition of bivariate data, just like we have defined last week, we say that sometimes when you're interested in getting information from two characteristics that affects a particular cause, a random variable. For instance, we said that if you are interested in the health of a patient, and we know that the health of that patient is characterized by, say, yes, ma, can you go ahead?
Yes. You gave us exercise the last class. Is it that we're going to treat it? I mean, further to the slide, or
Okay.
you give us hint because
The
I think
exercise.
yes.
Yeah, the exercise. Let's see. Let's finish today's class. Then
Okay. Okay.
next week, when we come in our next class, we'll now look at the exercise.
Okay. That's good.
Yes.
Thank you.
Well, have you gone through the exercise?
I did. I didn't really get to see if what I'm doing is meaningful because the example you gave us in class, the probability uh distribution on the event is already given. So
Yes,
all we
yes,
need to do is just add it up marginally. But
yes, exactly.
here we are. I have to construct the
You have to construct
probability.
it. Yeah.
So I'm
Yes,
not
exactly.
sure if what I constructed was meaningful because
Okay.
yes, that's why I wanted to go through it with you because the question is talking about the random variable for the number of CPs chosen and let okay no it's a construct a table of the joint probability for S and Y.
Yes,
Even though
yes.
we're given three professions, two
Mm,
is we are interested in two.
yeah.
So I don't know. That's why I said I don't know if the way the probability, I mean the way I constructed my probability is
Mm,
right. So that's just where the whole thing is. But I know what it takes to have a marginal probability. So
okay.
that's
Yeah.
it.
Yeah. Yes. Yes. There's no qualms about that. We will look at it in depth in the next class.
Okay, that's good.
Yeah.
I
But
will
the
appreciate it. Thank
yeah,
you.
that's what the assignment is saying. You should construct the joint
Yeah.
probability
All
table.
right. Yeah.
Yes. So let's forge ahead. So we've looked at the definition of the bivariate data. We say it involves two variables, and it's usually common in natural mathematics where variables like age and insurance claim are often analyzed together. So if in insurance, in natural science, when you want to analyze two variables like age and insurance claim amount, you can that's where the bivariate data comes into play. So a bivariate data is a data that is two-dimensional, like what we're explaining. When it is multivariate, then it is more than two. When it is univariate, that's it is one dimensional, then it involves only a variable, a random variable, say x. When it is bivariate, then it involves two random variables, say x and y. When it is multivariate, then it involves more than two random variables. So if we're interested in variables like age and insurance claim amount, then we are looking at a bivariate data. What are some importance of the relation of understanding the relationship between two variables? That's one important thing why we need to study the bivariate data. So because understanding the relationship between variables helps actuaries to make informed decisions, such as setting insurance premiums or assessing risk. All right, definition of bivariate data. Well, we have been defining, but we're just trying to get different perspectives so that we understand the definition. But we say bivariate data refers to a type of data that involves two variables, often denoted as x and y, where each pair of observations corresponds to a value of each variable. So oftentimes when we're talking about bivariate random variables, we're actually considering a pair of each variable, a pair. So we're actually considering a pair. So, but when we're from the pair, if we're interested in uh, one of the data, then it becomes we're interested in the marginal density. Now, some examples. Let's say in a study of students' performance, where X represents the number of hours spent studying and Y represents the corresponding test scores. So each pair of values, that's the value that the random variable can take, that's small xi and small yi, represents the study time and the test score for the ith student. So for the ith student, we'll consider the study time and the test score. So we're trying to see, maybe we want to see whether it corresponds. Maybe if he studies longer, if his time for study is longer, will it affect his test score? Or if his study time is very low, will it affect his or her test score? So we have two random variables there, and we're trying to understand their relationship. So that leads us to what we call covariance, variances, standard correlation, and so on and so forth. Now, in an experiment investigating the relationship between temperature x and the rate of plant growth y, so we want to see whether temperature affects plant growth. Each pair of values, small x subscript I and y subscript I, corresponds to a specific temperature and the observed growth rate for a particular plant. Yep. So notation, just like we stated last week, we use this particular notation is represented as ordered pairs. Ordered pairs, like I was mentioning earlier on, is represented as ordered pairs. So we have xi comma yi, where the xi represents the value of the first variable x, and yi represents the value of the second variable y. That's for the ith observation analysis. So, in analyzing bivariate data, where it often involves examining the relationship or the association between the two variables, and this can include calculating summary statistics, plotting graphs such as scatter plots that will show us that will just show us the juxtaposition of the two random variables, and fitting mathematical models to describe the relationship between x and y. All right, bivariate moments, which is our main topic for today. So, what's the definition of bivariate moment? What does it mean? Uh, how does it work? How do we apply it? And how is it useful in actuarial science and actuarial mathematics? So, a bivariate moment or bivariate moments are statistical measures that describe the distribution and relationships between two variables, often denoted as x and y. They provide insights into the central tendency, dispersion, and correlation of bivariate data. Like I was mentioning earlier on, we see the first moment, that's the first bivariate moment, is what we call the mean. The second moment is what we call the variance or standard deviation. The third moment is what we call the skewness, and so on and so forth. So we'll be looking at the measure of central tendency of the two random variables, their measure of dispersion, their that's which their covariance, and then also the correlation between these two data random variables. Now, types of bivariate moments. So we'll look at we'll look at this here and we'll understand what it means. Then we'll now quickly go to the other material I was talking about to see how these things are computed mathematically, even though we're not going to dive in depth into it, but we'll just see how they represent and how they are done. Then we will now come back and look at some examples and application. Now, types of bivariate moments. Now we see the mean. Mean bivariate means represent the average values of the two variables. The joint mean, that's mu of x. Remember, we say mu is the Greek alphabet used for population mean. So the mu of x and the mu of y, that's the mean of x and the mean of y together as an ordered pair uh, to show that it's a bivariate mean. If it were just a univariate mean, there wouldn't be this ordered pair here, but because it's a bivariate mean, we have this ordered pair here. So we say it denotes the center of the bivariate distribution. It denotes the center of the bivariate distribution. That's measure of central tendency for the bivariate distribution. Yeah. So the variance or the bivariate variance describe the spread or dispersion of the data around the means. Yeah. We know just like the normal variance, it measures the deviation from the mean or the dispersion from the mean. Same thing. When we're dealing with a two-dimensional random variable, when we're dealing with two-dimensional random variables, we're also looking at the spread or the dispersion of the data around the means, the two means. So here in this case, we have two means. Now they include marginal variances, which we have talked about last week, and that's what marginal variances sigma squared of x and sigma squared of y, as well as the covariance sigma xy. Yeah. So also the covariance measures the degree to which two variables change together. It indicates the direction and strength of the linear relationship between x and y. So the covariance actually measures the degree to which these two variables change together. Yeah. So it shows the direction of strength of the linear relationship between these two variables. Then the correlation coefficient, which is we are talking about actually talking about the moments. We have the first moment, the mean. We have the second moment, the variance. We have covariance, which is another moment. We have correlation, which is another moment. And so on. So the correlation coefficient, usually denoted by small letter r, or the rho, the Greek alphabet rho, is a standardized measure of the linear relationship between x and y. Now, it ranges from -1 to +1. So, when you are dealing with calculations in correlation, just like we must have been aware, it cannot be greater than 1. It can only the range of values is from -1 to +1. If it is -1, then there's a strong negative correlation, which means that as one is going forward, one is going backward, and the correlation is very strong. Or if it is positive, then we have a strong positive correlation. If it is less than 5, less than 0.5, whether positive or negative. If it is negative, we have if it is less than 5, we have a weak negative correlation. If it is less positive, we have and less than 5, we have a weak positive correlation. So where values closer to 1 indicate a strong positive linear relationship between these two variables, and values closer to 1 to -1 indicate a strong negative linear relationship, and values close to 0 indicate no linear relationship or a weak uh, relationship between these two variables. All right, so let me quickly stop sharing now, and then I'll go back. I'll share another file so that we will look at um, the calculations. That's how to we'll look at some of the mathematics aspect of it. We may not too go deep, but we'll look at it. Yeah, so I'll stop presenting and present another material. Then when we come back, we'll continue from here where we stop here. So I'm on it. So give me some few moments. Working on it. Yep. So can you see my screen now? Can you see my screen now?
Yes.
Okay.
Yes, I can see your screen.
All right. All right. Thank you.
Yeah.
So let me show full screen. So this material here, I'm going to share it to the to where it's like the write-ups looks tiny, right?
It's tiny, please.
Okay. Let me go back. I'm trying to add the size so that it will be more visible. I think it's better now, right? Yeah, I think it's better now. Sorry. Just some moments, please. Yeah, I'll just share from here without zooming the sharing full screen. I believe you can see it. Yeah. So let me scroll up. So I'm going to share this material. I'll share the material in the drive so that we'll see it more clearly. I'll share the material
All
in the
right.
drive. Yes, I'll share so
Okay.
that we'll just take our time and look at it properly. So these are this talking about the PMF of the bivariate distribution. Remember we defined it last week. Yeah, looking something like this, and this for continuous. That's why we're having an integral sign, like we explained last week, and then this is for the joint density function. We also explained last week. We were able to perform some calculation, and then for the marginal, we have this expression for it, uh, and then for I'm trying to navigate to where we have the moments so that we'll just look at the moments. Uh, ah, okay, yeah, I'm getting closer. So we have expectations and moments of functions of a random vector. So to get the expectation of yeah, I'll explain. I believe you will understand. So as you are seeing the expectation, we say we are looking at the expectation of a bivariate distribution. That's why we're having x and y here. Or you can simply represent it. This is like the product. You can simply represent it as expectation of x plus y. So they say this leads us to define the expectation of uh, any function g of x comma y of x and y, which makes it bivariate. So for us to get the expectation of a random variable, which is the mean, if you can remember, we say that the expectation is the mean, just like we did in the univariate random variable. But here we're having a bivariate random variable. We take the mean, and the mean is here the mean we say is the expectation of the function g of x comma y, which is a double integral, just like we did this last week. We got the mean. So the mean is actually the first moment. So once you do it, you have this function, and we know that it's finite. Yeah. So integral from negative infinity to positive infinity. That's double integral because of the x and the y. And then we have g of x comma y given f of x comma y dx dy. Yeah. So calculating the expectation of the sum as we have here, that's of g comma x, which is equal to x plus y. Uh, we have this function here. So as you can see, so we take the expectation and we sum the two random variable x plus y, and at the end of the day we have expectation is equal to expectation of x plus expectation of y. If you remember the value that we gave last week for this for the mean, we actually give the same value. You take the expectation of the first random variable and then you sum with the second random variable, and it gives you the joint uh, moment or joint first moment or joint mean of the bivariate random variable. Also, uh, we can also check all these things. We can also look at the product. The first one we look at is the sum. Here we have uh, the product moment, first product moment. So we can also do it this way. Oh, sorry. We can also do it this way, and then we get what we're looking for. Then also, so this is how we were able to obtain all those formulas that we're using. Then also when you do that, you get the covariance. So the covariance of x comma y is equal to the expectation of x comma y minus the expectation of x times the expectation of y. So once you get the expectation of x comma y, you now subtract the product of expectation of x from expectation of y. That gives you the covariance of x and y, which we have talked about earlier on. So this is how we do it. This is the mathematics behind it, and this is an example. So I'll share this material so that we'll look at it. So we want to get the covariance with this above example here. We say suppose x comma y has the joint probability density function given here, f of x comma y equal to 8xy if uh, x and y lie between 0 and 1 and 0 otherwise. So we have to compute the covariance. So we take the expectation first, and we have the expectation of y, we have the expectation of x 8 over 15 and expectation of y 4 over 5, and we'll compute the covariance of x and y, and then we'll go to the definition. By definition, we know that the covariance of x comma y is equal to the expectation of x y minus expectation product of expectation of x times the expectation of y. So when we do that, taking the integral to find this, we already have expectation of x, which is 8 over 15, and we have expectation of y, which is 4 15. So we can get the values here when we multiply, but we need the expectation of x comma y, the product moment, we need it here. So to get the product moment, we take the integral from the range of value 0 to 1 for 0 to 1 for x, then 0 to y for y, and then we have xy. When you integrate this, which I know is straightforward as we can see, when we do that, we get 4 over 9. Now bringing it back to the covariance, we already have 4 over 9 as our product moment. Yes, yes, ma'am. Yeah, you know, ma'am, you can go ahead. I can see your hands up.
The expectation of the product, I thought we
Yes.
said it's going to take value from 0 to 1 and 0 to 1. Why is it that we are doing it like marginal?
Okay, I don't understand. Explain more.
The expectation, we're given that 0 is in between, how will I put it? X and Y is
The
between
range.
0 and 1.
Yes. Yes.
So, but in this your product now, you're
Mm.
saying that it's 0 to 1 and it's 0 to Y. I
Yeah.
thought
Yes.
it's
See.
going to be
Yes.
0
Yes. Let me
to.
explain. You know, the how do I explain? For x, you see we have 0 is less than x,
Hmm.
and x is less than y, which is less than 1. So when we take the range for x 0 and 1, for y we will take sorry, when we take for x 0, when we take for y 0 and 1, for x we are going to take 0 and y.
Okay, I thought the first one was 0. I mean, it's minus infinity. I'm looking at it from the definition: minus infinity to
Okay, okay.
infinity, minus infinity to infinity of a f of I'm always, you see
Yeah,
though.
we have minus infinity to infinity and minus infinity to infinity as here.
So fx of y. Okay, I think that's where my confusion is, because you see what I'm saying now. Because if you
Mm.
look at the second line, x was first taken care of, so I thought it's going to be from 0 to y, because the interval is 0 is less than x less than y. and y less than 1. So I was thinking we're going to have 0 to 1 to y, and
Mm. And then 0.
0 to 1. That's the way I
Okay.
put at it in my
Yeah,
brain.
it's the same thing now. Whether you product is the same. Whether you bring
Mm, mm.
um this is whether you bring 0 to y first or
Ah.
0 to 1
And
first is the same thing.
like I said, it's good the way I pointed it out. That
Okay,
said,
okay,
I could have compute mine in that wise, but maybe there's something different there. That's why I
oh,
have
okay,
to speak out. I know
okay,
product
okay.
will end up giving me the same thing, but
Yeah,
maybe
yes,
there's
yes,
more
yes.
to it than, because I could have said 0 to y and
Mm.
then integral
0
0 to 1.
0 to 1. Mm.
Aha.
Okay.
So because the
Well,
first one now.
I'm sure if you compute it either way, it's going to give you the same uh
Okay.
value.
Okay. The
Yes.
first
So
one is 8y squared. Mm.
you want us to try
Okay.
it? I'm sure
I'm
it's something that
okay. It's like
okay.
we're
You want to look at it? Let me give
no,
you
I'm
some few
looking at
minutes.
it now.
Okay, okay.
Uh, because what we have there is sx.
Mm-hmm.
I mean 8xy. So to me,
Yes.
that's like saying x 8y squared integral s squared. So where okay, the 8 is common to. So we brought out the 8
To
and
both of
then
them
integrate it
from the
over
function.
y. Yeah, the first integration was over y. That's why we have, yeah, we have 8y squared 1 over 3. This is,
Confused?
yes, a bit confused because it's like, um, I don't know. If I'm to do it, I know the first this after the covariance, the expected of sy, the product. So
Yes.
the next line is like we multiply. We are saying sy 8sy will give me 8y squared and s squared. So
No,
I integrate.
if you are substituting, you have to substitute if you are substituting the value of y to be y here. Do you
Uh-huh.
understand? You are putting the value of y to be y here after your integration. This becomes y cube now.
That's fine.
Then divide over 3 into integration now. When you substitute, you have y cube.
Okay, so it's going to be naturally. Okay, if I integrate, if we look at the
Mm.
second line after the
Yes.
expectation,
Yeah, this one.
sy squared
Yes.
is taken to be part of the first. Now we want to integrate over uh, y. Is that or is it over there? So the first one
You know,
is over y. So if I integrate over y, this will give me 8y raised to power 3 over 3, the y. That I
mhm.
know.
Yes.
So why are we still
So
having
here
the
we're
integrated
integrating
over?
was we're
Okay,
integrating
and
was in the bracket first.
yeah, yeah,
You understand? And then we
yeah.
substitute b minus a. That's b. Our b is y. Our a is 0. That's the limit.
Oh,
We
okay. The
we
first one in
integrate this
bracket
first.
was taken care
Yeah.
of, and
Yes.
then
So integral of x squared gives us s cubed over 3.
okay.
Then when you substitute the value of y, it becomes y cubed over 3. Minus when you substitute the value of 0, everything becomes 0. So you have y cubed over 3. Take everything that is in this bracket first, this curly bracket here that you're seeing here,
Yeah, I got
gives
it now.
us,
I got it.
yeah, it gives us
So
y
the
cubed over
first
3.
bracket was integrated over s,
Yes.
but substituting the value.
Mm.
I mean the
Like
I
we
got it
explained
now.
last week,
I got it. I got it.
we are
Yeah.
factoring xy as a
Yeah, I
constant.
got it now. I got
Okay,
it now. Yeah,
all right,
because
all right.
I've seen it. The one in the bracket was first integrated,
Integrated first,
and
then
then
substituted.
we now substitute over the interval. So with
Yes,
0, it disappears. So y gives
yes,
us this. And
y cube
now
over 3.
after we got that, we now integrated over
Integrate with
y.
respect to y now, yes.
Yeah,
Mm.
that's it.
So
Okay.
it's clear, right? So
Yes.
now this gives us this
4 over
is
9. Yeah, I
yeah,
got it.
all right.
Yeah.
It's okay. Yeah, so doing that we get the covariance which we have here,
Mm,
and then this is another theorem here. Yeah. So we may not take so that we'll not spend all the time in the mathematics and then neglecting the
just to
practical. Yeah. So
refresh my memory.
oh
Yes.
yes, exactly. So we can I will share this material like I said. This is another theorem here. for the variance of the sum. Variance of x plus y is equal to variance of x plus variance of y. So when you do that, you take the expectation of x equal to mu x and all the proof. So we have that the variance of x plus y gives us variance of x plus variance of y plus 2 covariance of
S
xy.
Y. Yeah.
Yeah,
Two colons S Y.
yeah. So we have another example here that is talking about the marginal densities. We've already explained marginal densities last week.
Yeah. Yeah.
Yeah, so when we say marginal density, I believe you understand what we're talking about.
Yes.
Yep. So we have this function, this example is solved here. We have 2y, 0 elsewhere, and so on and so forth. So basically, when you go through this material, if you're interested more in the mathematical aspect of what we have, the mathematical aspect of it, you can get some more information here. Yes, so here also talks about the correlation and regression. Here's the formula for the correlation. Rho of xy, that's which is equal to covariance of x comma y over the root of variance of x times variance of y. So if we already know how to get the value of the variance of x, the variance of y, the covariance, which are all moments, we substitute it into the correlation, and then we get the value of our correlation. And remember, like we explained earlier on, that the correlation has interval -1 to +1. It lies between -1 to +1. Yeah, so there's also a proof for it. We can prove this value that we're seeing here, this correlation between x and y. Yeah, we can prove it. I think the proof is here too, if I'm not mistaken. And there's a proof for it. I think they use the Cauchy squares inequality here, and so on. So, in our maybe careless time when we're actually interested, so this also gives the conditional expectation of the function y given x, like we talked about in conditional probabilities. Yeah, when we're talking about the what's the name of this? You see that when
Yeah.
you have
Yeah.
an
It's
information,
conditional probability. Yeah. What Bayes theory, if I'm right. Hello.
so that we check. Yeah, you getting me?
Yes, you muted at a time.
Oh, okay, okay. Sorry about that. Yeah. So if we look at this material, we can get additional information, especially as it regards the mathematical aspect of it. So we look at the correlation, the regression, all those moments we have mentioned, the mean, which is expectation, the variance, the or the standard deviation, the covariance, the uh, correlation, the regression, the conditional probability, and so on and so forth. So we can find this material useful to give us some more information, especially where we get some of the formulas that we'll be using. All right, so permit me to quickly change the slide I'm sharing, or stop sharing and go to another slide. Uh, I think you can see the next slide now.
Yes.
All right, so let me zoom it so that we'll continue the from where we stopped earlier. All right. So we were here earlier on and we're talking about the types of bivariate moments. So we saw the mathematical aspect of it, and we looked at the bivariate means, which is expectation, the variances, the covariance, that's the sigma xy, the individual marginal variances, sigma squared x and sigma squared y, uh, then the correlation, and so on and so forth. All right. So now, in calculating and interpreting bivariate moments, we use mathematical formulas and statistical techniques, and these provide valuable insights into the joint behavior of these two variables. And in turn, it facilitates our analysis, our modeling, our decision making in various fields, uh, finance, economics, and engineering. We are actually looking at the actuarial aspect of it. Now, types of moments, we have the raw moments and we have the central moments. Now, the raw moments provide information about the spread and distribution of the data points, while example, when we have the second raw moment here, mu2 of 0 for age and insurance claim amount data. So here, when we say 2 0, we're looking at the 2 stands for the age and the 0 stands for the insurance claim amount. We're saying that The second, how do I even put it? Like we're saying that let's say if we categorize each in a particular, maybe we have the first grade, second grade, third grade continually, or when we have two pairs. Remember, we're talking about ordered pairs. So when
Yeah.
we have two pairs, hello, are you there?
Yes, yes.
Yeah. So when we have two pairs, that's two for age and zero for the claim amount. Uh, we're actually talking about the second raw moment here
I
as
thought
concept. So
second row moment is that not the variance?
the,
Second
the
moment.
second raw moment.
Okay, the raw moment is the main. Yeah.
Yes,
Yes.
yes, yes, yes.
Mhm.
Yeah. Then we
But
have
when
the
they said
central
spread, I thought
spread. Yeah,
spread
spread is
means variance. I don't know. That's the way I interpret it.
yeah. Spread means variance,
Mm.
covariance,
Yeah, so that's why I
standard
use
deviation.
the word second moment there.
Okay, okay.
Yeah.
All
So
right.
the
So the
central one is the mean around it.
yes, that yes, which deals with data points in the middle, right?
Yes. So
Yeah,
that's why it's central.
yeah,
So
that's why
once
it's
we
central.
spread, we're talking about the
The
what's it
variance
called?
and
The
the variance and
variance and the
the
covariance.
covariance.
Yeah.
Yes, yeah,
That's when you talk about the outliers and the stuff.
yeah, exactly,
So
exactly. So, uh, we use this for the calculation of the first bivariate first moment. Like I said, the first moment is the mean. Remember?
yes.
Yeah. So it's just this formula for the mean: one all over n summation x i's I ranging from one to n, which is if we know this formula now, normal formula of
Yes,
the mean.
yes, yes.
Yeah. So this is the mean for the
It's finding the mean of what's it called? A data set. Add everything, divide by the number. That's what they're
yeah,
saying there.
yeah, exactly. So the mu of x is the population mean for the first random variable, while the mu of y is the population mean for the second random variable.
Mm.
Yeah. So where xi and y subscript I represent the individual observations of x
Observation,
and y
yes.
respectively,
And
and
n is the
n
total number.
to
As
yes
I
total
said,
number
it's
of
just the
observation.
normal uh, mean formula.
Yeah. So yeah, even though now we're considering the two of them together.
Yes, but if you look at it, it's still related to the observation of each event. That's why it's an
Yes.
individual
Yeah,
observation.
exactly.
Yeah.
And since they are ordered pairs, then it means that their n will always be the same.
Yes.
Yeah,
Yes.
since it's an ordered pair, they are pair. So it means that if you're having 10 of the first random variable, you also
Yeah.
have 10 of the
It's just
second.
like the example you gave us regarding the is it actuary that want to work on
Exactly.
the accident in two different towns.
Exact. Yes, exactly.
So
Two different terms.
yes, if he's going to observe 10 in town A, then he has to observe 10
10
in town
in
B.
term
Yeah.
B2. Yeah. Correct, correct. Very, very, very beautiful. Nice one. So the bivariate first movement provides the average values of the variables x and y, representing the central tendencies of their
Mm,
distributions. It serves as measure of location around which the data points cluster.
cluster, yes.
Then also have calculation of the second central moment mu dash of 20 for age and insurance
Mm,
claim amount data. All right, so raw product moments. Remember, we showed that in what we are calculating up in that other material.
mm.
The product is when you have x times
And
y.
y multiplies
Yeah.
the normal
Yes.
product, what it means.
Yeah. Exactly.
Multiplication of the probability of S and Y.
Yeah. So that gives us the raw product
Mm,
moments. Yeah. So here we have an example is the calculation of the raw product moment mu 11 for age and insurance claim amount
mm,
data.
mm,
Then the central product moment measures the joint variability by considering the product of deviations from the mean.
mm, mm,
Yes. And then we have an example as the one below. Then relationship with covariance and correlation. So it's just a brief overview. Uh, co- covariance and correlation measures of linear association between two variables. That's what the
mm,
covariance and the correlation
mm,
does.
mhm,
Yeah, where the covariance measure the dispersion, the rate, the rate of dispersion. The correlation measures their relationship.
mhm, mhm,
Yes. So covariance and correlation can be derived from certain combinations of bivariate moments, like
mm.
we have explained in that material.
Yeah.
When you have, for instance, for the covariance. You remember when
Yes.
you can combine the product, when you have the value of the product moment,
Yeah,
and then the value of the
you
individual
find
moments,
the
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 difference.
mean of each one
Yeah, yes. Then
and
you
take
find
it away from the what's it called? The
the
square of the joint one.
yeah. Then also when you are looking for the correlation, remember the formula. We have the
Yeah, the row, yeah. I've forgotten
covariance of
over
xy
variance of this and that. Yeah.
over the square root of the
Yeah.
variance of x plus the variance of times the variance of y, something like that. No qualms. We'll look at the formula down and we'll see how we can
Yeah.
do that. But
Apply.
we say to get the covariance and the correlation is just a combination of individual uh, of certain bivariate moments. That's just it. Yep. All right. So we'll be looking at the example now. Uh, we say that in natural science or natural mathematics, we use these moments in insurance analysis to understand the relationship between variables like age and insurance claim amount. We also use moments, bivariate moments in insurance, in interpretation of insurance context. That's to inform decisions on pricing, on reserving, and risk management. Then, all right. So we'll look at practical example now of bivariate moments in actuarial science. So, like we know, we say that the covariance measures how much two random variables vary together. Like I explained earlier when I said the spread. Remember? Yep. So let's look at an example now. Example one or example, let me say example two. I think we have looked at one example of
Yeah, let's continue at least. The
so
name
let's
does not matter.
yeah, just the understanding that
Yeah.
matters. Let's consider two insurance related variables, X representing or the random variable X representing the number of claims
Mm,
filed by policyholders in a month,
mm,
and Y representing the corresponding that tells us other pairs,
mm,
total claim amount in dollars.
yeah,
Suppose we have the following data for a portfolio of policies. So
mm,
for the number of claims, we have 5, 8, 10, 6, 7. And the total claim amount we have 2,000. That's in dollars, 3,000, 4,000, 2,500, 2,800. So if we look at it ordered in as an ordered pair, 5 corresponds to 2,000. So we're looking at a situation whereby we have 5 claims and the total claim amount is 2,000. Here we have 8 claims and total claim amount is 3,000. 10 claims, total claim amount 4,000. 6 claims, total claim amount 2,500, and 7 claims, total claim amount 2,800. So we want to see their covariance
mm,
and also look at the correlation. Now, to do that, we know the formula for covariance between x and y,
mm.
which can be calculated using this formula.
So you
The
find the mean.
summation, yeah, summation I ranges from 1 to n of
This
xi
really
minus.
throw me back to my university days. I did a lot
Oh,
of work
okay,
like this.
yeah, yeah. Yeah, that's cool. So you find the mean for the x,
But yeah,
you find the that's for the number of claims,
yeah.
then you find the mean for the claim amount,
Mm-hmm.
then you subtract each from
From
you
the
actually
mean.
do yeah from the mean. You
Yes,
actually do a
each one
table.
that it gives you the spread. Yeah.
Yeah, it gives you the spread. So you actually do a table to get to make it simpler.
Yeah, that yeah, you do it if it's plenty, but with this one you don't even need much of a table. But
Yeah,
it's
exactly.
neat.
Since
It's neat when you use the table.
yeah,
Very neat.
exactly. It's neat.
Yeah.
It's neat, and sometimes maybe easier.
Yeah.
That's if you can confuse if you are someone who confuses easily.
Mm,
When you use the table, it makes the work a lot easier.
mm,
Yeah. So once you do that, you get the value of x, the mean for x, the mean
mm,
for y, and then you find the deviations, and then the product of the deviations as well. Then over n minus one. Yep. So when we do that for this our value, yeah, here is it. So to get the mean, you
can
can
you
see, right?
remind me why one is always taken away from I remember
Yeah, because it's sample. We're looking at the sample.
yeah, one is always taken away from the
The
population.
sample, yeah, it's a
Yeah,
degree of freedom.
yeah, yeah. It's
Yes,
because of
degree of
the
freedom.
degree of freedom. Yes.
Mm. But
So
if we are dealing with the population,
yeah.
then we use n. We don't
Mm-hmm.
take away my
Yeah.
one. But yes,
Yeah.
but when we are dealing with sample, then we subtract one from the
Mm,
number of observations.
mm,
Yeah,
yeah.
and the reason why they do that is because when you are dealing with the population, you don't risk losing any information.
Mm,
That's why we call it degree of freedom. Let me just delve in a bit. When you are dealing with the whole population, you don't risk losing any information because each and every member of that population will be
it's
affected.
important. Yeah.
Yeah. Now, but when you're taking a sample, it may be that some information might be lost. So that's why to control for the degree of freedom, you
Mm.
now subtract one.
Yeah, I remember. I just want to remind myself of the because naturally we should have used n, but we are using n minus one because it's a
Yeah.
sample space and because of the so I just want a kind of quick reminder of that reason anyway.
Okay. Yeah. Great. Great. Yes. So, from what we're explaining using the formula for the covariance,
Yeah,
we can get the
it's
mean.
clear. In all
This
fairness,
is
it's
very clear.
clear.
Yes. We
It's
get
very clear.
7.2
Yeah.
for the mean for the number of claims. We
Mm.
get three thousand and sixty
Yeah. Then
dollars
take
for
it
the
away
claim
from
amount.
each individual.
Yeah.
And
Take it away
just
from
like what the
individual.
formula says anyway, that's one
Yeah.
good thing about mathematics. You can
Yeah. So
recall the
final.
formula and you know
Mm,
the method, then you get the answer.
yeah.
Except if you are
Exactly.
watching.
Yeah. Correct. Correct. Nice. Yeah. So this looks straightforward, right?
Oh, very. That's what I'm saying. If you like I said, that's what I said. Remind me of the reason why we're taking one away. So that's the only thing there. But if you go back to the formula, it's you're doing exactly what the
Yeah.
formula says there. Yeah,
Everything is clear.
yeah.
So, so here we now have the covariance between x and y as
Mhm.
1,583. So I think,
Yeah.
uh, what can you say concerning this interpretation?
If I look at the what's it called, the um the mean for the claim amount
Yeah.
is 3068. So if the covariance, the spread is too much, in all fairness.
Okay.
So
Okay.
looking at it just like that, it doesn't look like that when you say okay, 5 claims 2000, 6 claim 25, 7 claims 28. So I think, and then 8 3. Yeah, it's true. The spread is much.
The
If you
spread
look
is
at
much,
it,
ba?
yeah,
The difference is the difference is
yeah,
much.
the spread is much because at the time there's a 500, there's a 300, there's yeah, there's a 300, there's a 200, and there is a 1000.
There's a
And I think
1,000. Yeah.
that 1000 really sweep the whole thing off.
Yeah. Exactly.
Mm,
Exactly.
so the spread is much.
All right. So we can further it, right?
Yes, yes, yes.
So we can, from the information above, we can also go ahead and calculate the correlation coefficient. We'll see their relationship, whether they have a strong correlation or a weak
Coefficient.
correlation
Yeah.
or a negative relationship or positive relationship.
Mm,
Yeah. So if we do that and
mm.
using the standard deviations of x and y, we have the formula for the correlation. Remember when what?
Yeah, yeah, the
Yeah,
covariance over, yes, I
x comma
remember.
y over the
Mm,
product of the variance of x and the variance of y.
mm,
Yes, and the variance of x is given by this value,
mhm,
then the variance of y is given by this value.
mm.
Remember, this is
Yeah,
this
yeah,
is m
no, don't
minus
worry.
v
If
here.
I'm confused, I'll call your attention.
Okay,
It's
all right.
clear.
Yeah, I'm
Yeah.
trying to explain because of those who may watch the video
Okay,
later.
okay,
Yes,
okay.
yes, yes. So this gives us 2.19 for the uh,
Variance
uh,
of S.
variance of x, and then we have 578.47 for the variance of y.
Variance of
So
Y.
let's put it back into the formula since we already have the covariance. So we'll find the
Mm,
correlation and then we'll make our interpretation. Now putting it back into the formula, remember we got the covariance as 1,500
mm,
and
mm. 83.
1,583.
1583, yeah.
Yes, and then we'll fix it here, 1,583 over
The
2.19
2.19 times
times
578.47.
578.47.
Okay.
Now fixing it, we have this value. So we
Yeah.
have 0.470. zero,
Mm.
which is a weak
Yeah,
positive
it's
relationship.
not above 5.
Yeah. So now, in fact, it even confirms our covariance.
Mm. Mm.
Remember, you were saying that the spread is
It's
too
a bit
high,
much, yeah.
it's a bit much. So here we have a weak relationship,
Mm.
which means that the number of claims does not actually connect with the claim amount.
Mm.
You understand? So that's what it actually means.
Mm.
That the number of claims is too far. You understand?
Mm.
From the claim amount. So the
It's
correlation coefficient,
relatively okay,
yeah, is
zero
yeah,
point
but
0.4, because if we approximate it, it's 0.5. But like
yeah,
I said,
but it's still
it's,
weak, sha.
yeah, it's weak.
Yeah,
But in
exactly.
as much as it's not negative, it's weak because it can
Yeah,
take from -1 to 1.
yeah, exactly. So this is a weak
Yeah,
positive correlation.
yeah.
So the correlation coefficient between x and y is approximately 0.40470, indicating a moderate positive linear relationship between the number of claims and the total claim amount.
So this means that, just like you said, if the you see the claim amount variance, the spread at the bin is not much.
Yes,
So if it's not much and we apply it here, then the value will be high. So there's a
yes.
kind of inverse relationship between.
Relationship, yeah,
Yeah.
exactly.
Do you get it
Exactly.
now? Yeah.
Yeah, I get it. I get it. Yeah, and I like relating with you because you're understanding the thing from the mathematical aspect and just so fast.
Yeah.
Yes.
It's such a shame that they when you're studying mathematics, they just throw to your face all formulas
Yeah,
and
you
they don't
not.
relate it to real life.
Yeah, exactly.
Yes.
Nothing like a practical something. They just
Yes.
go
So
straight to
yes. So just the
calculation.
formula and the formula, like I said, all those proofs then I
Mm.
know about them, but there's never a time that somebody was trying to relate it to a kind of insurance company. And I don't really blame, because the our culture, we are not really into insurance. We are just getting there.
Yeah,
So
exactly.
as that's what
Exactly.
is happening, because uh, I think it was when I bought my car that I realized that there's insurance, even though you're hearing
You
about it, but you don't relate. But
don't relate.
yeah, but here, or let me say, in the developed world,
Mm.
right from when you're buying your phone, even any little thing,
Okay.
they introduce insurance to you. So you're really
Wow.
aware of what the product is all about. So applying
Yeah,
it is very easy. But even
it's very
an
easy.
average professor does not have not even really gotten insurance before over anything. So
Exactly.
that's what
So it's
is really,
abstract. It's abstract to
it's
him. So
abstract. They keep
yeah.
giving us abstract, abstract. So we, like you're saying it now, it's easy for people who has been into insurance or this or that. So they know, they understand. That's
Mm.
just, but it's their word. But it's not
Yeah.
in our word. So we keep studying. And that's why everything is a bit hard for us, because it's that we're
Mm.
studying things and we couldn't relate it to our environment.
Exactly.
That's it.
Exactly. Exactly. Yep. Yeah. So thank you for that. So let's further it. Now we have another example which looks similar to
To what we have.
the one what we already have. So
Three.
from there we'll
So
just look
this
at the
will be,
example.
yeah, this
Yeah,
will
we'll
be
just
a
look at
bit
the example.
better now, because the difference is not much to
The
look at.
difference is not much exactly. We have
Yeah,
12, 18,
it's
24,
just three, three,
15.
three, three.
Mm, Yeah, is it
Yeah, three,
12?
three, three,
Yeah,
three,
3,
three,
3,
three.
3, 3.
See?
Yeah. This looks somehow perfect, but let's look at it
No,
once and
it
see.
won't be perfect, but it won't be far. That's just what I'm saying.
Yeah,
Yeah,
yes, yes. Maybe whether negative or positive.
it should be. Let me see. Five.
I should give you time to calculate.
No, it's gonna be, because like you see now, when it's
Mm.
4, 12, when it's 5, 15, when it's 6, 18, when it's 7, 21. So it's a positive relationship.
Somehow, yeah, it's
Yeah.
somehow exactly, exactly.
So it's easy. Like I said, now you know what you're doing. Like before, they will put SI, S2, S3. So you don't even know what S is. You keep
Yeah, they
looking
put
at
X eyes
everything.
and Y eyes.
And why high, high. So that's just the main thing.
Yeah. So it's alright. So let's watch ahead.
Yeah.
So we have this with the corresponding other pairs. Number of accidents claim amount. The other one, we look at number of claims and the corresponding claim amount. Here we're looking at the number of accidents and the corresponding claim amounts
Yeah.
as an ordered pair.
Mm.
So calculating the covariance
Mm.
using the same formula, covariance of
And
x
the
comma
yeah
y is equal
method,
to the
the,
difference, the
the mean and
deviations,
then
yes.
the deviation. Yeah.
Yeah. So doing that, we calculate our mean first for the number of accidents. Then we calculate our mean also for the number of claims
Claim
for the claim
amount.
amount.
Yeah.
Yep.
So
Then
it's what I'm
we
saying,
get it.
3.75, you see?
We get the deviation. So we have 3.75.
You see, it's not far
Yes.
from each other.
So the now the
The
covariance is
coefficient,
3.75.
correlation
Mm.
coefficient here.
So now let's get the correlation coefficient. Inputting it back into our formula
Mm-hmm.
and obtaining what we already have. We have the
Do you see what I'm
variance
saying?
of
Do you see the
x.
answer now? I'm not
Yeah,
surprised. It's zero
mhm,
point 0.9. Very, very
0.968.
close to 1.
Very, very close. So it is, if you
You see?
approximate it, we will give you one
Yeah.
positive. Yeah. So in this case, there's a strong positive
Yes.
relationship between
Yeah.
the
So we
number
are
of
looking.
accidents.
The good thing about this one is that now they are using this or what the Python and Co are using. So the good thing is that if the data is much, then
Yes.
because we
Mm.
look at this data, sample data, we could easily read it about. Imagine if we are
Yes.
dealing with 1,000, or let's even be sincere, let's deal with like 200, 500. So I
Yes.
will not be able to see the correlation properly.
Just like that, by
Aha.
mere by
By
mere
mere
observation.
comparing just what I did then.
Yeah.
So
Even when
that's
you want to
why.
do the even when
Sorry.
you want to do the computation, it looks intensive.
Yes,
Yeah.
it
Time
will. It
consuming
will.
and
In fact, you can,
time
for you
wasting.
to even compute the variance. I don't know how many pages of paper you used to, if it's like 200. And so these
and
are what
and
they,
you most likely miss some
you will
values.
miss it, of course. So
Yes.
this, and it's a shame as we are learning the formula, the people that brought it to us are learning machine languages. So before we get to machine language, now I don't know. Okay, now they're learning AI. So you see, we're just moving.
Well, yes, when we have not finished learning the machine
Eh,
language now, we are now in AI.
we are now in AI. So that's the main thing. So we are always a step backward as a result of the fact that this is not what we are naturally relating to. This is the whole
Yes.
world. This is the way they operate.
Yes,
As in,
exactly.
yeah.
Exactly.
So they ensure that they equip themselves ready for a lot of things.
Exactly.
Mm.
Exactly. Mm. Yeah. So this one I think is it does not need
No, it's
much to interpret. So we
yeah.
have 0.9, which is a strong positive. So the correlation coefficient between x and y is approximately 0.968 to three
Mm,
significant figures, indicating a strong positive linear relationship between the number of accidents and the corresponding
claim
claim
amount. Yeah.
amount. Yeah. So uh, we're done with today's class. I don't think we have any exercise for today. Maybe I'll see within the week
No,
and try
we
and
might
get some
have to solve
exercise and
that
send.
one first so that
Mm,
we won't. I always love orderly. So, like you said, it's orderly
mm.
correlated. So,
Yes,
so
yes,
that when I'm going
yes.
through my notes, I will know that
Yeah.
okay, this one is taken care of.
Yep.
Yeah,
Exactly. Exactly.
but that
So,
will be next class, like you said.
do you have any question from
No,
today's
I mean
class?
I've been part of the class from the start to the finish. So, and I've engaged
Yeah, we have
myself
we have
deeply.
we
So,
have we have actually collaborated, and the class was
yes,
very interesting.
so I'm okay.
Yeah. All right. So, thank you very much for being part of the class.
Not a
So, in
problem.
our next class, we
Yeah.
will look at that assignment, that exercise.
Okay.
Yes, for the last class, and then we'll see what we can make of it.
Okay.
Then we'll look at the next topics that we have, the next course content that we have,
Okay.
and then we'll go in that manner. So I believe now we are beginning to we understand the probability theory and distribution, especially as it regards actuarial science
Yeah.
and actuarial mathematics, and then we see how those things actually work mathematically and theoretically. Uh,
Okay.
and then I'm sure when we are in our other classes, like the risks
Risk
management,
analysis, yeah.
yes, risk analysis and evaluation and the rest. We are seeing how these probability distributions are relating to what we are doing there
Mm,
and how they are practically practically how they practically relate.
mm,
Yes, so I'm sure that we are getting more equipped and more knowledgeable about these things and
yeah.
how they work. Yes. So
I will
thank you for
appreciate it
listening.
if this material can be downloaded tonight, because that's one thing. Though,
Okay.
yeah, is in fact for people who miss the class,
Yes,
it's
yes, yes.
always been helpful for them, for people that
Mm.
miss the class.
Usually, I think it takes about 24 hours for this to be ready
So they
in the
say, but
drive.
if
Yeah,
you
that's
if
just the
it's being
challenge.
started tonight, then by tomorrow those that miss the class can go through. And
It can go through.
yeah,
Yes,
it's
exactly,
always good,
exactly.
since we
Mm.
have less people in class now, so
Mm.
to help them to
Yeah,
update
exactly,
themselves very
exactly.
well.
So I'll also send that other material this night. I'll send it this night
Yeah.
in the drive, so you can
Okay.
locate it in the drive. Yeah.
Okay.
Thank you for being part of the class.
You're
Yeah, the
welcome.
attendance is taken.
Aha.
Yes.
Anyway, I don't, for the past two few lectures now, no attendance. Maybe
Yeah.
because I'm the only one. So
Yeah. Yes. Exactly. Exactly.
okay.
Mm. So
All right
it's all
then.
right. Have a
Thank
great night
you. Thank
and
you,
have a
Jacob.
wonderful
God
week ahead.
bless you. I
Yeah.
do
God
appreciate.
bless you too. Amen. Amen. Yeah.
Right. Bye. Bye.
Bye, man. Mm.
Yeah.